My topic of presentation in inorganic chemistry is the chemistry of noble gases. Where are these noble gases present in the periodic table? These are present in the 0 or 18th group on the right side of the periodic table. The elements in group 0 on the right of the periodic table are called the noble gases. The group of noble gases is regarded as 0 or 18th group in the periodic table. These are at ordinary temperature and do not have any chemical reactivity. Due to their chemical inertness, they were known as inert gases. Helium, neon, argon, krypton, xenon, and radon. These all comprises of noble gases. Nowadays, as number of compounds of these gases, particularly of xenon and krypton, have been prepared. This shows that these gases are not completely inert. In the earlier time, these gases were known as inert because there was no chemical reactivity shown at that time. They are called noble gases instead of inert gases, which signifies that these gases have some reactivity. Because of the low abundance of these gases on the earth, they are also known as rare gases. मैंडलीव के टाइम पे जब उसने पीरियडिक टेबल को डिज़ाइन किया था तो उस टाइम पे नोबल गैसेस का कोई आइडिया नहीं था बिकॉज वो रिएक्टिविटी शो नहीं करते तो उनके कंपाउंड्स भी नहीं होने चाहिए थे, तो इसलिए कोई भी कॉलम लेफ्ट नहीं था नोबल गैसेस के लिए. तो ऑब्वियसली ही कुड नॉट इमेजिन द एग्जिस्टेंस ऑफ एलिमेंट्स विच हैव almost no chemical reactivity. That's why Mendeleev had no left any spaces for noble gases in the periodic table. But after some time, Ramsay, the discoverer of these gases, proposed a new group for these elements on the basis of their atomic masses and lack of chemical reactivity. This group is called zero group of the periodic table. The zero group also suggests chemical inertness or zero valency of these gases. Before the discovery of noble gases, there was a sudden change from the most electronegative halogens on the right hand side to most electropositive alkali metals left hand side in the periodic table. The addition of zero group is between 7A and first A group has solved this anomaly. The position of noble gases in the periodic table was later confirmed by Moseley, who constructed the periodic table on the basis of their atomic numbers. The values of atomic numbers of noble gases strongly suggest that they should be placed after halogens and before alkali metals. That's why they were put there. Now, physical properties of the noble gases. Elements are given. As we know, the outer electronic configuration of helium is 1s2, neon is 2s2, 2p6, argon 3s2, 3p6, krypton 4s2, 4p6, xenon 5s2, 5p6, radon 6s2, 6p6. From this screen, we saw that van der Waals radius is increasing down the group, and the force of attraction is also increases down the group. The first ionization energy of these elements is very high because they do not show any valence electrons. So due to their stable condition, the first ionization energy of these elements is very high. Ionization energy decreases down the group. Now melting point. They have low melting point. Down the group, melting point increases because the force of attraction, van der Waals force of attraction, increases down the group due to their large sizes. Boiling point also shows the same thing. Chemical inertness of noble gases. Here are the reasons why these noble gases show chemical inertness. The atoms have stable completely filled electronic shells. उनकी इलेक्ट्रॉनिक जो ऑर्बिटल्स हैं वो completely filled हैं. There is no unpaired electrons there. जो फर्स्ट आयनाइजेशन एनर्जीज हैं केमिकल नोबल गैसेस की वो बहुत ज़्यादा है. The noble have almost zero electron affinities. Due to their very stable condition, they do not gain any electrons. So their electron affinity is also zero, almost zero. Therefore, they do not have any tendency to gain, lose, or share electrons with other atoms. Chemical properties of noble gases. The atoms of inert gases have saturated shells, therefore, they are chemically inert. Recent studies have shown that under certain specific conditions, they enter into chemical combinations and form some rare chemical compounds. The specific conditions and the types of compounds formed by these gases are discussed below. Under excited conditions, sparking helium at low pressure in presence of mercury, tungsten, etc. forms compounds like Hg, He2, WHE2. Helium compounds are also formed in discharge tubes like BiHe2, FeHe, PT3He. These compounds are not considered as true chemical compounds as helium is absorbed on their surfaces. Compound forms through coordination. Argon forms a number of unstable compounds with varying number of BF3 molecules. For example, ArBF3, Ar6BF3. In these compounds, argon atoms donates a pair of electrons to boron atom of BF3. In case of higher compounds, fluorine atoms of BF3 also donate pairs of electrons. Hydrates of noble gases. The hydrates of these gases are formed by compressing the gases into water. For example, Xe6H2O. Compounds formed by physical trapping, that are clathrates. The inert gases argon, krypton, and xenon form solid compounds with certain organic molecules, such as phenol and hydroquinone, under pressure. In such compounds, the inert gases are enclosed in the crystal lattice of organic compounds known as clathrates or Keech compounds. Compounds of noble gases. Xenon forms a large number of compounds with oxygen and fluorine. Because the electronegativity of oxygen and fluorine is really high, they are able to gain the electrons. These are xenon fluorides, xenon oxides, and xenon oxyfluorides. First compound, that is xenon difluoride. Its preparation is xenon difluoride is the best prepared by heating the mixture of xenon and fluorine in molecular ratio of 2:1 at 400 degrees Celsius in a sealed nickel tube. xenon और फ्लोरीन को हम डायरेक्टली ऐड करेंगे. उसका टेम्परेचर जब हम 400 डिग्री सेल्सियस करेंगे और निकल की प्रेजेंस में जब हम ये रिएक्शन करते हैं तो XeF2 बनता है, xenon difluoride. On cooling quickly, a colorless solid XeF2 is obtained. Properties. Now we are going to study what are the properties of xenon difluoride. First, xenon difluoride is a colorless, crystalline solid and its melting point is 129 degrees Celsius. Second, it reacts with hydrogen to give hydrogen fluoride and xenon. When we react XeF2 with hydrogen, we get xenon and hydrogen fluoride. It gives substitution reaction with strong protonic acids. Xenon difluoride, when we react it with HX, where X can be ClO4 negative, CF3COO negative, SO3F negative, etc. Then we get FXEX plus HF. When FXEX plus HX is reacted, the products are found to be XeX2 and HF. Fourth, it hydrolyzes slowly but completely in acidic, neutral or alkaline solutions. When we react 2XeF2 with 2 moles of H2O, we get 2 moles of xenon plus 4 HF plus oxygen. When we react 2XeF2 plus 4 NaOH, we get 2Xe plus 4 NaF plus O2 plus 2H2O. Fifth, it oxidizes iodine in the presence of BF3 to give IF. When we react xenon difluoride with in presence of BF3, it oxidizes I to give IF. Second, XeF4. Here the oxidation state of Xe is +4. So there can be compounds of +4 state XeF4, XeOF2. So let's see the preparation of XeF4, that is xenon tetrafluoride. It is prepared by heating a mixture of xenon and fluorine in a nickel vessel at 400 degrees Celsius under pressure of 5 to 6 atm. It can also be synthesized by passing an electric discharge through a mixture of xenon and fluorine at -78 degrees Celsius. So here are the two ways by which we can prepare XeF4, that is xenon tetrafluoride. Now let's see the properties of xenon tetrafluoride. It is a colorless crystalline solid with melting point 117.1 degrees Celsius, sublimes readily. Oxidized by hydrogen to HF at 30 degrees Celsius. A stronger fluorinating agent than XeF2. ये XeF2 से ज़्यादा strong fluorinating agent है. Then the next compound we'll see is XeFe, xenon hexafluoride. Here xenon is in the oxidation state of +6. So let's see the preparation of xenon hexafluoride. It is prepared by heating xenon with excess of fluorine in the molar ratio of 1:20 in a nickel vessel at 250 to 300 degrees Celsius under pressure of 50 to 60 atmosphere. So Xe plus 3F2 is equal to XeF6. This is the one way where we can prepare this xenon hexafluoride. Second way is it can also be obtained by the oxidation of XeF4 with O2F2 under pressure. When we react XeF4 with O2F2 at -130 degrees Celsius, we can get XeF6 plus O2. Now let's see its properties. Crystalline substance. Its melting point is 49.5 degrees Celsius. Mostly volatile. All the fluorides of xenon are greenish yellow. Color vapor. It is extremely reactive. Therefore, it cannot be stored in a glass or quartz vessel because of the following reactions which finally give the dangerously explosive xenon trioxide. So, when we react xenon hexafluoride with SiO2, it forms 2XeOF4 plus SiF4. When we react 2XeOF4 with SiO2, we get 2XeO2F2 plus SiF4. When we react it again with SiO2, then we get 2XeO3 plus SiF4. XeO3, xenon trioxide. It is very explosive compound. Very dangerous explosive compound. Second, it reacts with fluorine ion acceptors to form adducts. When we react XeF6 with PtF5, we get XeOF4 plus PtF5 is equal to XeF5 positive ion, PtF6 negative ion. When we react XeF6 with SpF5, we get XeF6.SpF5 equal to XeF5 ion SpF6 negative ion. When we react XeF6 plus AsF5, it gives XeF6.AsF5, which is equal to XeF6 positive ion AsF6 negative ion. Now XeOF4, fourth compound. Preparation of xenon oxytetrafluoride. First, xenon oxytetrafluoride is prepared by partial hydrolysis of xenon hexafluoride. When we react XeF6 with partial water, it gives XeOF4 plus 2HF. Second, by the action of xenon hexafluoride on silicon dioxide, when we react 2XeF6 with SiO2, it gives XeO4 plus SiF4. Soon as the yellow color of XeF6 disappears, the content are immediately quenched with the solid CO2. It is done to avoid the formation of XeO3, that is explosive, as XeOF4 plus SiO2 is equal to XeO3 plus SiF4. Now the properties of XeOF4. First, it is a colorless compound. Its melting point is minus 46 degrees Celsius. Second, it is reduced by hydrogen to xenon. When we react XeOF4 with 3H2, it gives Xe plus H2O plus 4HF. Third, it reacts with water or silica to form another oxyfluoride, XeO2F2, in which xenon remains the same oxidation state. Further reaction gives explosive compound XeO3. Fourth, XeO4 plus H2O is equal to XeO2F2 plus 2HF. XeO2F2 plus H2O is equal to XeO3 plus 2HF. 2XeOF4 plus SiO2 is equal to 2XeO2F2 plus SiF4. 2XeO2F2 plus SiO2 is equal to 2XeO3 plus SiF4. Now the fifth compound is XeO2F2. Let's see its preparation. Here also xenon is in the oxidation state of +6. So first is by mixing XeO3 and XeOF4 at temperature close to minus 78 degrees Celsius. When we react XeO3 plus XeOF4 at minus 78 degrees Celsius, it gives 2XeO2F2. This compound is purified by fractional distillation. Second, it is also formed when XeOF4 is hydrolyzed or reacted with silica. 2XeOF4 plus SiO2 is equal to 2XeO2F2 plus SiF4. XeOF4 plus H2O is equal to XeO2F2 plus 2HF. Now let's see the properties of XeO2F2. First, it is a colorless solid. Second, its melting point is 30.8 degrees Celsius. It is easily hydrolyzed to give xenon trioxide. When we react XeO2F2 with water, it gives XeO3, that is unstable compound and very explosive. Sixth, XeO3, xenon trioxide. Let's see its preparation reactions. Xenon trioxide is prepared by the hydrolysis of XeF6 or XeF4. When we react 6XeF4 with 12H2O, it gives 2XeO3 plus 4Xe plus 24HF plus 3O2. When we react XeF6 with 3H2O, it gives XeO3 plus 6HF. It acts as a powerful oxidizing agent in acidic medium. For instance, it oxidizes Pu3 positive to Pu4 positive in the presence of H positive ions. 6Pu plus 3 plus XeO3 plus 6H positive is equal to 6Pu plus 4 plus Xe plus 3H2O. Now the seventh compound is XeO4, xenon tetraoxide. Let's see its preparation reactions. Here Xe, that is xenon, is in the oxidation state of +8. It is prepared by action of concentrated H2SO4 on sodium or barium xenate, that is Na4XeO6 or Ba2XeO6 at room temperature. Na4XeO6 plus 2H2SO4 is equal to XeO4 plus 2Na2SO4 plus 2H2O. Now let's see its properties. It is very unstable and decomposes to xenon and oxygen. Now let's see the structure of some xenon compounds. XeF2, that is xenon difluoride. Its oxidation state is +2. Melting point is 129 degrees Celsius and its structure is linear. The next is XeF4, xenon tetrafluoride. +4 oxidation state. Melting point is 117 degrees Celsius. Its structure is square planar. Next is XeF6, xenon hexafluoride. Its oxidation state is +6. Its melting point is 49.6 degrees Celsius. Its structure is distorted octahedron. Next is XeO3, that is xenon trioxide. Oxidation state is +6. Melting point, it explodes readily. Structure pyramidal tetrahedral with one corner unoccupied. The next compound is XeO2F2, that is xenon dioxy difluoride. Its oxidation state is +6 and its melting point is 30.8 degrees Celsius. Its structure is trigonal bipyramidal with one position unoccupied. XeOF4, xenon oxy tetrafluoride. Its oxidation state is +6. Its melting point is -46 degrees Celsius. Its structure is square pyramidal. The next compound is XeO4, xenon tetraoxide. Its oxidation state is +8. Melting point is -35.9 degrees Celsius. Its structure is tetrahedral. Next is XeO3F2, xenon trioxy difluoride. Oxidation is +8 and melting point is -54.1 degrees Celsius. Its structure is trigonal bipyramidal. XeO4, xenon tetraoxide. Oxidation state is +8. Melting point is -35.9 degrees Celsius and structure is tetrahedral. Then next is Ba2XeO6-4, that is barium perxenate. Its oxidation state is +8 and its structure is octahedral. Now let's see significance of noble gases in development of theoretical chemistry. First, in elucidation of distribution of electrons in atom. Second, in periodic classification. Third, in the development of electronic theory of valency. Fourth, in radioactivity. So these were the significances of noble gases in development of theoretical chemistry. So that's all for today. Thank you.